There's a very important conceptual leap to be made between thinking of a fluid as a collection of particles and thinking of a fluid as a continuum. Now obviously a fluid is anything that flows, but let's consider a beaker of liquid. We could think of this as being made up of a whole load of molecules, and if we take one of these molecules out here and look at it, we could say that each of these molecules has a certain velocity, for example, that is defined on the molecule itself. So that's one way of looking at it. The problem with this way of looking at it is that in order to do any calculations you've got to consider all the molecules in the beaker, and there are so many of those that that becomes entirely impractical. So what we can do instead is say, let's imagine a region of the beaker, so some volume of it there, and look at the average velocity of all the molecules in that. And that, of course, is now defined at a point in space. So there's our fundamental difference. In this continuum model, things are defined at points in space, whereas in the molecular picture, things like velocity are defined on the molecules themselves. And now, instead of thinking of the individual molecules, we look at all this stuff inside here and call it a continuum fluid. It's just, if you like, a continuous lump of stuff with no gaps in it, and it has certain properties like density, viscosity, and so on. And these properties here are determined, of course, by the molecular nature of the fluid, by the particular molecules that it's made up of. But once we've worked out what they are, once we've worked out what the viscosity is, for example, we then treat this as if it's a continuum fluid, rather than worrying about each individual molecule. Now I want to think first of all about this thing here, the average velocity being defined at a point in space. And obviously in order to average over the molecules we have to have enough molecules for this average to be meaningful. Let me just, as a different example, take a road with a car on it, rather strangely shaped car, and I'm going to draw the molecules as before, and I'm going to imagine that they're very, very widely spaced around this car. The question is, how close together do the molecules have to be for us to speak meaningfully about an average velocity at a certain point around the car? Well, what we can think about with the molecule is how far it goes before it hits another molecule. That is called the mean free path. And it's generally given the symbol lambda. We need to compare that with a typical distance of the car, a characteristic distance of the car, which I'm going to call L, and it's the length of the car here, although it could be its width as well. And we need to basically make sure that the mean free path of the molecules is very much less than a characteristic distance of the object that we're looking at. Now this is often looked at in terms of the Knudsen number, which is defined as lambda over L, and it of course has to be very much less than 1. Now it's a very good question what's meant by very much less than. So what we can tend to say is that if we look for where the Knudsen number is equal to 1, we know that at that point the continuum model will have broken down and we can no longer speak meaningfully about averages because there aren't enough molecules.